The inverting configuration is we have an op amp, and it has this infinite gain. It multiplies the difference between the non-inverting and the inverting pins by an infinite amount, which means that any difference will blow up to plus or minus infinity here. Now, a real op amp won't have quite infinite gain, but it can be very high, like 100,000 or a million. And so if there's any difference between these two, that will result in a, relatively speaking, very large voltage here. And if we have a large voltage here, we have a voltage divider back to here. Of course, we have this voltage source here, but we can solve that loop all the way around, going through ground, back up around to here. So if we have a large voltage here, that means we've got a divider, and that voltage is going to get divided down some. And this amplifier amplifies the difference between these two. And as we amplify a little bit of that negative difference, we will bring these two nodes together. Now, this one's forced to ground. The non-inverting is at ground. So that means any difference that remains between these two will meet with increased voltage on the output, which will cause increased or decreased voltage on the output, which will cause this to end up to be the same as this node. And we say by these little dots here, I mean that we have a virtual short. It's as if we have these two nodes connected by a wire. It's not connected by a wire. There is no current flowing through them, but the voltage here is exactly the same as the voltage here. And if this voltage is ground, then it's easy to calculate everything. So if we have R2 equals 10, so we've got 10 ohms up here, and R1 equals 1, then this gain equation, which we did last week, which is the gain V out over Vn, is minus R2 over R1. So our gain would be minus 10 over 1 equals minus 10 volt per volt. And that negative sign means that this amplifier is an inverting amplifier. It means if we supply plus 2 volts, the output will be minus 20 volts. If the input is plus 0.1 volts, then the output will be minus 0.1. And we can understand that as being a phase difference, or just saying it's inverting. So it's that sign means that we are inverting. It also means we're 180 degrees out of phase. So if you think about a sinusoid, if we had an input and an output versus time, we had an input like this, and if the gain was set to be 1 or some number, then we would be perfectly out of phase. Right? We'd have the same frequency signal, just when the input is low, the output will be high, and when the input is high, the output will be low. It's 180 degrees out of phase. Oh, sorry, I shouldn't do that. I'll slide this over here. So the nice thing about having these resistors here for feedback, or one of the nice things, various nice things, but we could buy very expensive resistors and control to 1% or 0.5% or 1/10%. We routinely at Keysight used to trim resistors to less than 0.5% to a few 1/10% routinely, and they were in op amps and in circuits like this. So we can, and resistors are cheap, and even precisely built resistors are relatively cheap, and so we can control the gain of this within very tight tolerances by using something as simple and cheap as a resistor. And also resistors don't change much with temperature, and they don't change much with time typically, or we can buy resistors which don't change much with temperature. And And so it becomes stable with temperature. The resistance value doesn't change with voltage, so it's stable with voltage. It's stable with frequency. It's stable over years. So we have a mechanism for establishing gain on this amplifier, which is very stable. The gain of the amplifier itself is very poorly controlled. If you make 1,000 op amps on a semiconductor wafer, you'll have 1,000 different gains. None of them will be identical. They'll all vary for various different reasons. But it would be relatively easy to control the resistance to a much better value. In a sense, we can say that we've tamed the infinite open loop gain of this op amp. We've tamed it with these resistors in this negative feedback network. There's some other pretty big benefits as well. So there's more to negative feedback than just stability, but that's a very important one. Yeah.
So I remember you saying that there's a virtual short between the terminals of the op amp. Does that only happen when there's a feedback resistor, or is it always?
So the question is, there's a virtual short between these, and does that happen only when there's a feedback resistor? Yes. It only happens when there is a connection from the output back to the inverting pin. If you have a connection from the output back to the non-inverting pin, you'll have positive feedback and the thing will blow up. It'd be an oscillator at best. But if you don't have any feedback, if there's no connection from the output back to the inverting input, then you will not have a virtual short. And you should always be able to look at a circuit, and if it's an op-amp circuit, and you can see negative feedback, or any other kind of circuit, if you can see negative feedback, then you can start to understand what's happening very quickly. And that should trigger some thoughts in your brain if you see feedback. Now, a real op-amp doesn't have infinite gain, of course. And I touched on this some yesterday, so I was a little bit ahead yesterday of where I was today, so sorry about that. But so the real gain of an op-amp is very big, make no question. So the 741 has got a gain of a couple 100,000 minimum. The OP27 op-amp in your kits has a minimum gain of 1.5 million. So op-amp gains can be really, really big and can feel a lot like infinity. And in fact, that's one of the important things about them, is we can make them with such a big gain. But if we no longer have infinite gain, the question might be, does it really work? So we've got the circuit. So we've got R2 and R1. And an op-amp that does not have infinite gain. So that means, so I said we have VID, which is V2 minus, well, let's say it's inverting gain, or inverting pin, is V plus minus V minus. And that equals V out over A. But now this gain, so if it's infinite, then that says that the difference between these two has to be 0. That's what that says. If the gain of this op-amp is infinite, then that's going to force this virtual short and cause these two terminals to be at the same voltage. But if A is not infinite, then this is no longer 0, right? It can't be 0. If the gain isn't infinite, then there is some value that we could calculate. If the gain is 1.5 million, it means that it's 1.5 million times the difference will be the output. It can't be 0. It could be very, very small. And the question is, do we care about that? So One thing is for sure, though, this is always 0 volts. That's ground. If we have this connection here from the non-inverting input to ground, that means absolutely this node is 0 volts. No, there's no question about that. That's 0 volts. The question is, what is this node? What's the voltage up there? So this is 0. Oops, I should change color. Well, so that's a 0. It's a plus. That's 0. So what we're saying is that the inverting pin is equal to minus V out over A. And then we can find the current. We know that I1, that's that current, is equal to Vn minus the inverting pin over R1. And it's exactly the same thing. We can do some math. I wanted to do it for you, but they got some algebra trick in there. I'm not exactly sure what that trick is. And after a while, I decided I don't not want to know what that trick is. So we can find the gain with A is not infinity. So with a actual op amp, and I gave you this. I wrote this equation yesterday. If A is not infinite. Now, if A is infinite, then we divide this quantity by infinity. So that means this is 0. And if this is 0, then we have minus R2 over R1 divided by 1, which reduces to minus R2 over R1 if A is infinity. So it's just a correction, really, or a more complete version of that gain equation. But if you have a finite gain, you need to use this equation to understand exactly what's happening. And I think I gave some examples of that yesterday and showed you how it becomes, this inverting pin is really, really close to 0. So this is 0 here, and for sort of vaguely real numbers, this could be microvolts or picovolts or nanovolts or something just really tiny. It can be very, very close to 0. and for all purposes, it does. Let's just say it equals minus R1 over R2 for a reasonable real op amp. What we need to have is we need to have 1 plus R2 over R1 over A to be much less than 1. When I try to make that little marker show up, it doesn't always show up, and sometimes it becomes stupid. So to make this gain equation, minus R2 over R1, which is what it is for an ideal amplifier, we just need to have this bottom reduced to 1, which means that this quantity over here, 1 plus R2 over R1, and I've got another something funny in it there. There's no minus sign in there. For reasonable real op amps, it will be a design goal of theirs is to make it so that the gain for whatever kinds of R2 over R1 ratios they might expect to have happen will be much less than 1, so that the gain reduces to R2 over R1. And values like 100,000 are kind of typical. So I've noticed it almost appears as if they hurried the 8th edition into print. And of course, I have the earliest possible edition because they gave it to me a while ago. And your editions may have some things corrected. I haven't gone to look for an errata, but there should be some errata. I found some various odd things in it, but in particular, there's kind of like a massive typo around section 2.3.3. The words don't match. It says they're going to say one thing and then they do something different. And in fact, they're skipping a whole bunch of stuff. So the text doesn't actually discuss the input resistance or the output resistance of the amplifier, and it doesn't discuss the non-inverting configuration at all. It just goes on to the next section after 2.3.3 as if you know what the non-inverting configuration is. So I'll discuss both those. It doesn't take very long, but in general, for amplifiers, we always want gain, whatever that looks, whether we're looking for the amplifier or the system itself, input resistance, Rn, and output resistance. We always want these three things. And so, and sometimes they're real easy, but we always want to find those three things. So for the non-inverting configuration, one thing we're trying to find is what is the resistance seen by the signal source looking in. Let me draw it as a signal source. We're always interested to know what is Rn for Vn. Right? What does this signal source here, Vn, whatever that is, and it has its own output resistance too, right, or a source resistance, but ignoring that, calling that 0, we're interested to know whatever we plug in to this amplifier. So we have an amplifier right here. Oops. Well, this is the amplifier system. And we want to know what the input resistance is and what the output resistance is of that amplifier. And the output resistance is what we see looking back in. So there's always a virtual short inside the op amp, right? Because we have negative feedback. So we have a virtual short. That means that the input resistance looking in to here is easy to find because we've got 0 volts on the non-inverting input, which means the inverting input has 0 volts. So we've got 0 volts right on this node there. And the circuit is just looking into this end here. We've got ground here, 0 here, and we're trying to find the resistance looking in. It's just R1. That's all it is. For the inverting configuration. That's actually, so that's easy to find. It's really easy to find, but that's actually a very big problem for the inverting configuration. So we want to have a large input resistance. A small input resistance means this inverting configuration will require current from this voltage source. Having a small resistance means we may have quite a bit of current flowing through there. If we have current flowing through there, we have voltage drop. If we have much voltage drop, it means that this signal may become weaker and weaker. And so that's a real problem. We want to isolate this amplifier from the two sides. You could imagine this inverting configuration. Maybe this is the input on a oscilloscope. Well, the input on an oscilloscope, its input impedance is often like 10 mega ohms, right? And if we wanted 10 mega ohms input resistance, R1 would have to be 10 mega ohms. And if we wanted 100 gain, then this would have to be 1,000 mega ohms, 0.1 giga ohms, and big resistors are really expensive. And they also add noise to circuits. And so, and it might not even work. We might not get enough current to go through it to make it work right. So it's hard to get large input with the inverting configuration, and it's really problematic. So to find R out, we need to look inside the op amp. So inside the op amp, what we really have is a voltage source with 0 output resistance. It's a short there, remember? It's just an amplifier. In general, we have a Thevenin circuit inside here. This is a Thevenin representation, and what we're saying is that R out is 0. And that means if we're looking inside this amplifier, that R out, that's the same as looking at something that has a 0 output resistance. So R out is 0. That's good. That's great. That's a very useful, important, powerful feature of an op amp. That means an ideal op amp can drive infinite current, right? It doesn't care whatever load you put out there. It will drive current until the output voltage is what it's supposed to be. That's great. Now, an actual op amp, of course, can't source infinite current. Often they're limited at 10, 20, 30 milliamps, something like that, although you can get high-powered ones. You can get high-powered op amps that can drive a stereo, or you can get low-powered op amps that can't drive much of anything. But most of the ones that you buy in chips and the ones that we'll use in labs and stuff often can drive 20, 30, 40 milliamps if you look at their specs. And that means basically it behaves like this up until it hits 40 milliamps, and then it just won't put out any more. So it just reaches a limit, which is different from saying it has a output resistance. It's as if its output resistance is 0 until it hits 40 milliamps, and then its output resistance is infinite, or not infinite. It just can't put out any more, which is kind of a little bit different. And it's also important to realize then, because this op amp can drive lots and lots of current, it can supply lots of current, that means that this feedback network doesn't have any impact on the system, because this op amp, what's inside of there, can drive plenty of current, and it can drive whatever load it's feeding, as well as the feedback network. It's got the ability to drive both. So that's a couple things the book is skipping. Another thing is the non-inverting configuration. So the non-inverting configuration is still using negative feedback, so fundamentally it looks the same. We still have V out here, and we have R2 and R1. And when you see that configuration, you know that there's a virtual short between the inverting and non-inverting pins. Right? We know that there has to be that virtual short because we've got negative feedback, right? That connection from output to input tells us that this virtual short is existing. And what the virtual short means is that this inverting pin or node is going to follow the non-inverting node. And so if we put the input here on the non-inverting pin and just connect this other end of R1, connect it to ground, then we have an amplifier with negative feedback, but the input is being driven off of or onto the non-inverting pin. Now, this ground may make you nervous. You may have this image that current can only go into ground, but current can go either way from ground. So if we need to supply current this way, ground can supply infinite current. It can handle a lightning bolt, positive or negative. It can supply or soak up tons and tons of current. So we can have current going in this way, or we can have current going in this way. It doesn't upset ground either way. It'll drive whatever current we need. It's ideal from that standpoint. And this voltage is going to follow this voltage, which is Vin. So we're going to have Vin on this node. Instead of having ground on this node, we've got Vin, but we've got ground over here. So it's still easy to calculate out what's happening. So we still have, because of the virtual short, the difference between these pins is still being amplified by A, and that means the difference is driven to 0, which means the virtual short is operational. Ideally, but again, like we did for the inverting configuration, it works out so that in a real op amp, it's very much like that. So the feedback is forcing this inverting pin to follow the non-inverting pin, just the same way that the inverting configuration did. So now V minus, I should also say that's, let me just write that as the inverting pin is now, by the virtual short, forced to be the same as Vin. And that means that I1, oops, I1 is equal to minus V inverting over R1, which is minus the non-inverting pin over R1, which is equal to Vn over R1, and that all equals I2, because still we have no current going into the op amp, right? The Rn of the op amp itself is infinite here and here, so no current flows in there. The input resistance of this amplifier system is R1, but if we're just looking at the op amp itself, this ideal op amp, the input resistance looking into the inverting pin and the non-inverting pin excuse me, is infinite. Neither of them soak up any current.
Dr. Lindsay, is that a negative right in front of the V plus?
Yeah, I probably missed a, so that's a negative, so that's a negative. So this equals V minus V out over R2, which is equal to Vn minus V out over R2, because it equals I2. These two currents are the same. So then we can say that minus Vn over R1 is equal to Vn minus V out over R2, which is equal to Vn over R2 minus V out over R2. And so if we move these around, put all the V-ins on one side and all the V-outs on one side, because we always want to write an equation that has V-out on one side and V-in on the other side. So we have V-out over R2 is equal to V-in over R2 plus V-in over R1, which is equal to V-in times 1 over R2 plus 1 over R1. And we've got this R2 hanging out over here, so we can multiply that through both sides. I'll keep that on this page. So then we've got V out is equal to Vn times R2 over R2 plus R2 over R1, which is equal to Vn 1 plus R2 over R1. And always, to find gain, we want to divide output by input. So the gain is V out over Vn, which is 1 plus R2 over R1. Very similar to the inverting configuration, except now there's not a negative sign. There's a plus sign. I'm making a mess out of everything. So it's not inverting. The inverting configuration had a negative sign, minus R2 over R1, and then we have this 1 plus. So the gain is slightly higher for the non-inverting configuration compared to the inverting configuration. So if you believe the math as you follow it through, then you believe that this is what it's doing. Then you should believe that the gain of this amplifier, V out over V in, is 1 plus R2 over R1. If you believe the math. So that's why I wrote it in, because to me the derivation is pretty clear and pretty easy to understand. To kind of look at it and understand what's going on, it actually is kind of weird to understand what's happening, both in the inverting configuration and the non-inverting configuration. It's kind of like, wow, really? Is this what's happening? But the math is very easy, and knowing KVL and KCL and Ohm's law and the simple algebra, it's like, yeah, okay, this has got to be what it is. This is just how it is, and so that's how I think about it. Input resistance and output resistance are easy to do, so I'll do it right on here again. Output resistance is the same of that whole amplifier. It's the same as on the inverting configuration. We're just looking inside this amplifier, and it has 0, so it can supply any current it needs. Input resistance is what this source sees, and Rn is infinite at low frequencies anyway, especially for MOS, because there's no current flowing in. So I can open circuit inside that op amp. So the input resistance is infinite, which is very good, and the output resistance is 0. So in a lot of ways, what we want to always use is the non-inverting configuration because it's so much better. So we can make a nice circuit, a non-inverting a buffer. So if we've got this circuit here, so if we've got a non-inverting configuration, if we force, or if we just connect this, make that 0, right? If we have, if we shrink the size of R2 to 0, then the gain is equal to 1 plus R2 over R1, which is equal to 1 plus 0 over anything. We can put any value of R1 there, it doesn't matter. We've got a 0 on the top, so this is 0, which means the gain is equal to 1. And in fact, it doesn't matter to have this resistor there at all. We can have any value we want, and this node here is going to be exactly the same as the output. And so that one's gone, but we still have, we always have that, right? We still have the virtual short. So that means that the virtual short it's forcing the output to exactly follow the input. Right? The output is connected back like this, and this amplifier will supply any voltage it needs to cause this difference to be 0. And to cause that difference to be 0, it needs this voltage to be the same as the input, and that means that the input is directly applied to the output. That's the same thing as the gain being 1, right? If the gain is V out over V in equals 1, and that says that V out is equal to V in. It's a circuit which directly connects the output to the input, but doesn't actually connect it by a wire. It's as if, I will say this, but the text doesn't say it or anything, but there's also a virtual connection. The output equals the input. That's what this buffer means. But there is no actual connection. There is no current flowing between them. So they're isolated. We could have a very weak voltage source on the input, and the output will be just fine. It will exactly follow the input. Or we could have a huge load on the output, and the op amp can drive that huge load on the output. No, because with the inverting configuration, it wants to, so with the inverting configuration, you're saying what happens if we make 0 over R2? You have a gain of 0, so it won't do anything. So it has to be this way, the non-inverting configuration, and we can just draw it like this. We just connect the inverting pin to the output with a wire. It doesn't matter what R2 is or R1. Doesn't matter what this is, so we can just delete it. If we plugged in R2, it'd have to be a resistance of 0. And we could plug in any value of R1. it just might require some more current. So if we put in a 1 ohm resistor there, it would mean this output would have to drive current through that 1 ohm to maintain it so that this node stays exactly equal to the input, because there's that virtual short always. Buffers are really, really useful. They, I've seen senior projects fail because they didn't put a buffer in a circuit. And if they'd come and ask me, they'd say, yeah, we got this problem because our output is getting loaded down, or is loading down our source driving it, and it can't supply enough. It's like, well, you know, the final presentation is the wrong time to ask me about this problem. If you'd asked me a little earlier, I would have told you, we'll just put a buffer in, and then you would be fine. And you just have to make sure your buffer is fast enough. Buffers are really, really easy to construct and make, and you may find a use to even use buffers in your in the lab. So if you have the Digilant analog discovery, or you have the ADLM 2000, either way, the wave generator can only drive about 10 milliamps. And sometimes you need more current than that. One way to get more current is just hook a buffer up, use one of your op amps, hook it up as a buffer to the wave generator, and feed for that op amp, just feed the output back to the input, the inverting input, and plug your wave gen in right here. And now you'll have a much stronger output that can drive maybe 40 milliamps, and that might make your life a lot easier. And some op amp packages have multiple op amps in them, so you just put one package in, put a couple of buffers there, and suddenly you've got a lot more power that you can drive, and you don't load down the input source. So I think I might include that in some labs of the analog discovery people, just because it's so useful to have more current driven out of your wave generator. 10 milliamps is a really, it's not enough current for some things. So another thing you can do, another thing that they used to show, which they don't show anymore in the book, I think because they think it's I don't know, they were just trying to delete stuff. It's a weighted summer. So what's happening? You've seen weighted summers in action, I'm sure. If you've ever been to a concert, you've seen one working. Or if you've seen pictures of a recording studio, you've seen them working. That stuff these days is more likely to be digital, but there's lots of old stuff lying around. So we have the inverting configuration, and we'll call this RF now for feedback. We have V out, V minus and V plus still. We still have a virtual short, and now we'll call this R1, R2, R3. We could have more of these. We could have as many as we want, and we have VI1 and VI2 and VI3, and like that we can have more. And we have a current IF, and we have a current I1, current I2, and a current I3. So KCL, you think about KCL right there, it means that IF is equal to I1 plus I2 plus I3, right? We've got all these sources are in parallel, so their currents are all adding up, and they're all going through here. The current into the inverting node is 0, and to the non-inverting node, that current is 0. So this current is exactly the same as the sum of these. And if you work out what's going to happen, we'll have V out is equal to minus RF over R1 times VI1 plus RF over R2 times VI2 plus RF over R3 times VI3, so on and so forth. It's the inverting configuration, right? But we're summing up these inputs. These inputs we're summing them up, and we're weighting them by the ratio of RF, which is the same for everything, and these individual resistances. So you could say RF is a master volume. If you made RF into a potentiometer with just one, just using half the potentiometer, then you could change, you'd have a variable resistor, and you would change the output, the gain of this entire op amp, right? So one knob changes the volume for all channels. And R1, R2, R3, those are individual channel volumes. Right? And so you could individually have a whole bunch of inputs coming in and change those, adjust those, and you could also change all of them with one knob. That is the same big, huge board you've seen in concerts, right? Every time you ever go to a concert, there's always some guy or some group of people in the very best seats in the whole house, usually, sitting. Sometimes they're up on a little tower, right? But they got the best place, and they got this big board with all these knobs and controls. And this is what they used to be in the 60s and the 70s, the 80s, the 90s. Well, 90s is when the transition occurred, I suppose. But for a long time, those control boards were exactly this, a weighted summer. An op amp with a feedback resistor and a whole bunch of variable resistors. It was, more op amps. They've made it a little more complicated, but fundamentally, it was no more difficult than this. And they're just a bunch of variable resistors. Plug in various microphones into these inputs. If you need 2 channels, you make 2 of these. And so they'd have a big board with a whole bunch of pots all over it that are just adjusting those weighted values. And you see old ones in garage sales, and people buy those. You can make that easily out of a digital circuit these days. So these days it's likely to be digital, although I suspect that there's a number of musicians that don't like. Well, it's not suspect. I know there's a bunch of musicians that are real Luddites. They don't like modern technology, and they don't trust digitization, and they want to keep things analog. And so I'm certain you can buy high-end ones just like this, still brand new. You can buy cheap ones, but and high-end ones also. Yeah, master volume. Yeah.
Okay.
It's like a master volume. Yeah, that's RF over R3 times VI3, and then 3 little dots. All right. So on the other hand, I think the book still includes integrators and differentiators. The reason to include those, so we'll get there eventually. The reason to include those is not because we would make those circuits still, although you can, and they do happen. Used to be able to make, and still can make, an analog computer from them. The reason to include those is because they point out what happens with real circuits, because those involve capacitances, and real circuits have capacitance. We'll get there. So an op amp is a difference amplifier, right? So you're saying an op amp is a difference amplifier. You're right. It's absolutely a difference amplifier. So we have V out equals VID times A. But the problem is A is huge, poorly controlled, both from op amp to op amp, and for different values of voltage, and for different temperatures, and as it ages, it changes. So it's not well controlled. It changes, and it's huge. So an op amp all by itself will apply an enormous gain to any difference. So it is a difference amplifier, but if we want to find the difference between a 50 millivolt signal and ground, we don't want to use an op amp because that infinite gain or gain of 100,000 says we'd have 100,000 millivolts, and that's too much. So, so if we use feedback and combine the inverting configuration and non-inverting configuration, then we can get there. So and if we do that, if we combine in the inverting and non-inverting configuration, then we could build something from stable resistors. So if you think about this split system, that's not the way I wanted to draw that. It's not the way I wanted to draw it either. So if we've got, if we're viewing the inputs to an amplifier as this split kind of system where we have a common mode voltage source, and then we have, which is the average of the input signals, and if we apply half of the signal and add it and half the signal and subtract it to get two different signals with an original signal difference, then that's what we have here. So we're adding and subtracting one. So then the amplifier as V out is equal to AD, the differential gain, times the differential voltage, plus ACM times VICM. So I have AD is the differential gain times the difference in voltage, and ACM is the common mode voltage gain times the input common mode voltage. And we want a big we want that to be big, and we want this to be small, and well, we just want it to be small. If we're making a difference amplifier, we only want to amplify the difference. That's what the difference amplifier needs to do. It shouldn't amplify the common things, just the difference. And a metric for seeing that, or how well we are doing, is the common mode rejection ratio, which is defined as 20 log, LOD 20 log of the differential gain over the common mode gain. And if AD is much bigger than ACM, then CM RR is big. And that's what we want. So we want numbers like, 50 to 100 dB, something like that. Those are the sorts of numbers that we want. So we're going to use a combination of the inverting and non-inverting configurations. Inverting. Is there a question? Huh? I'll post these. The inverting gain is minus R2 over R1, and non-inverting is 1 plus R2 over R1. So we need to get rid of this 1. This 1 is trouble. If we get rid of this 1, then we can make a difference amplifier with the two combinations of these. This one and this one, they're both R2 over R1. So we just need to reduce. We could either boost the gain here or reduce the gain here. And there's an easy way to reduce the gain here. We're not reducing the gain, we're reducing the effect. And if we just make a little bit smaller input signal to the non-inverting amplifier compared to the inverting amplifier, then we will we can balance it, so we just get rid of that 1. And we'll have the same gain but opposite sign. So we could do this with an amplifier with 1 op amp. So we have the inverting configuration. And then we have the non-inverting configuration. So we have, what am I going to call it, VI1. And then we're going to have VI2. But what we want to do is we want to reduce the value of VI2 by that factor of 1. So we can do that with a voltage divider on the input. And if we set those values of those resistors nicely, it will work out very well. Whew. So we've got the same configuration. As we've just now got, we now have a inverting amplifier here. Why does it do that? It's because I didn't have the color of this thing correct. If I get that color correct, then I can touch here. If I don't have the color correct, I don't know what that means, but it means I can't use the laser pointer. If we make this gain and this divider, the gain on this one match up nicely, then we will have a good difference amplifier. So what we're saying is we need equal gain. So we're saying that R4 over R4 plus R3, that's this non-inverting side divider, times the non-inverting gain, which is 1 plus R2 over R1. That has to equal R2 over R1. We need those magnitudes to be the same, right? And so then we can say, or you can do some math, and you can say that R4 over R4 plus R3 is equal to R2 over R1 over 1 plus R2 over R1, and that equals R2 over R1 times 1 plus 1 over 1 plus R2 over R1, which is equal to R2 over R1 plus R2. And if we set if we make R4 over R3 equal to R2 over R1, then the gains are matched. So that's how we got to do to make a nice difference amplifier, is set those gains equal. And by setting those gains equal, we'll be able to take the difference. So always, though, what we need to find is gain, Rn, Rout. That's always what we're looking for. We're always looking for those three things: the gain of a system, its input resistance, and its output resistance. So to find the gain, we can use superposition. It's not very hard, actually. So we can use superposition because we've got two linear circuits, the inverting side, the inverting amplifier, this input forming the inverting amplifier, and then the non-inverting side, and we can solve those two separately. And we know how to do both those. So we can find those separately. I suppose I actually have time to do that. So we've got V plus is equal to R4 over R4 plus R3 times VI2. So then we would have a V out so we'd have V out 2 is the non-inverting gain of that signal, R4 over R4 plus R3 times VI2 times the non-inverting gain, which is 1 plus R2 over R1. And we have an inverting gain, which is just V minus is equal to well, I don't want to write it that way. That'll be confusing. We can just say V out 1 directly. We know it's minus R2 over R1 times VI1. That's the inverting side. And the non-inverting side is exactly the same, except we've got this divider to reduce the input voltage a little bit. So then we can combine them. So V out total is V out 1 plus V out 2, which is oh, and if we set we set R4 equal to R2 and R3 equal to R1, then we have R2 over R1 times VI2 . If we set those the same, then we will have a gain or an output gain of V out 2. And so V out total is V out 1 plus V out 2 which is equal to minus R2 over R1 times VI1 plus R2 over R1 times VI input 2, which is R2 over R1 times VI2 minus VI1, and we have a difference amplifier that's perfectly doing what we want, and we have a differential gain of R2 over R1.